So, comparison between wireless body area network with the other networks. Body area network, the range of wireless body area network, it works within a few meters, like 1 or 2 meters, not more than that. And then wireless personal area network, the range is bigger than wireless body area network. And then the wireless local area network, the range is again bigger than this. Wireless metropolitan area network and wide area network. Then 3-tier architecture of W-band. So in a W-band, we have attached a lot of sensor on the body of the network. So who will take the sensor information? So coordinator node is responsible to collect all the information of the person from collect all the information from this sensor, and then via the access point, it will connect it to the internet, and in internet we store it in a cloud storage, and from that doctor can access the data, medical server can access the data, any family member of the patient can access the data. So this is a 3-tier architecture. First tier architecture is the person. Second tier architecture, they have considered the access point, which are helping in transmitting the data from this access point or router to the internet. And the third tier architecture is this application, like doctor, any medical personnel or family member can access the data from directly from the cloud. So communication in the W-band. There are 2 types of communications are possible in case of wireless body area network. One is intra-body communication, another is extra-body communication. So in case of intra-body communication, the information handles on the body between the sensor or actuator and the personal devices. So intra-body communication means I have attached some sensor on my head, on my feet, or on my near the heart, etc. I have attached, and these sensors are collected the information with the coordinator node. So intra-body communication, the sensor will transfer and receive information and coordinate with the personal like coordinator node. So the information handles on the body between the sensor and the coordinator node. Whereas in extra-body communication, the communication is done between the personal devices and the external network. As I'm saying that personal devices means my smartphone, it is sending all the information to the cloud. Okay, external network, that is extra-body communication. So one is intra-body communication and another is inter-body communication. So intra-band, we generally discuss all the communication related to intra-band communication because we are doing wireless body area network. Extra-body communication will not take care about. So nodes on intra-body communication are organized in a star topology or a 2-hop away from the coordinator node. Means if I generally need at most 2-hop communication when I am doing communication in intra-body communication, because my body size is how much? It is not very big, yes or no? So that I need multi-hop communication. If I have only one node, at most we use generally 2-hop communication in wireless body area network. It is already researched by many researchers, and we follow star topology. Star topology means I can keep mobile phone in my pocket and all the nodes are connected. So I am keeping my mobile phone in such a way all the sensor node will connect to my mobile phone via Bluetooth communication and send information to the smartphone. Okay. So IEEE 802.15.6 communication standards are used in case of wireless body area network, and it at most it supports 2-hop topology to communicate. The next is how wireless body area network is different from wireless sensor network. So wireless body area network is a subclass of wireless sensor network. Okay, and how it is different from wireless sensor network? You can ask why it is they have given a different name if wireless sensor network is already exist. So devices have limited energy resources in the wireless body area network. I can't implant like a heavy device on my body. Yes or no? It is difficult to carry. So that is another reason these wireless sensor nodes are very small, and because they are very small, the battery is also limited energy. So, but the recharge or change the battery. So, but I have implanted one sensor node within the skin of a person. So, to recharge it, I can't operate a person again and again if the battery will die. That means it is impossible. Like you have kept one sensor in an agricultural field or in a forest or anywhere, then it is easy to change the battery frequently. After 2 days you can change, after 1 day also you can change, but it is not possible to change the battery whatever sensor you have used inside the body of a patient. It is not frequently, you can't change. So computational power and available memory of such devices are also limited because they are very small. So computational power will be very small. You can't import on server on it. Yes or no? Big server. So this computational power and available memory of such devices are very limited. No redundant devices are available. Suppose in case of wireless sensor network, I kept multiple sensors. So if one sensor will die, then I can transfer information. I can take information from other sensors, which is not possible in this type of network because you can't implant many sensors inside the body. But if one will not work, then other will work. It's not like that. So no redundant devices are available, and extremely low transmit power per node is needed to minimize the interference and pop-up with the health concerns. So whenever you are implanting the sensor inside the body or maybe outside or inside, you have to see the consequences of it. Yes or no? So you can't implant more sensors if it will also radiate something while transmitting or receiving. So it may affect the body of the patient also. So you have to take care of that too. So the devices are located on the human body that can be in motion. So whenever we have implanted any sensor on the body of a person or body of a patient, that patient can move. That patient can move. That is mobile. And because it is mobile, what is written? W-band suffers frequent change in network topology. So I have attached one sensor on my hand. Suppose wrist, I have attached one sensor. Means I have wear one smartwatch. Okay. So whenever I am walking, my hand will go back and forth. So when hand will go my back and forth, and I have kept my coordinator node inside my pocket or maybe here a pant pocket or shirt pocket. That means the communication range, the topology will changing frequently. I can't say this is a static topology. It's a dynamic topology. Similarly, you have attached one sensor on your leg or on your feet. So while you are working, the topology of the body, this sensor network which frequently change. So we need very efficient routing protocol to communicate our data from one node to the another node. The data mostly consists of medical information, hence high reliability and low delays are required. Next is energy crisis in W-band. As I already said that dynamic path loss, data redundancy, data latency. If I am sending, suppose now my heartbeat is some XX degree, and because I'm sitting here continuously, my heartbeat is same for the like 1 hour XX, and I am sending my sensor is reading all this data. I'm sending those information to the coordinator node, and after a certain time, coordinator node will send all those information to the cloud. That means I am sending redundant data, and my battery will die after some time. Okay, that is energy crisis. Next is data latency. Sometimes some data are very very crucial for medical health application. So if it will take a longer duration of time, then it is of no use. Why I will wear my smartwatch if I will get data after 1 hour or 2 hours? It's not required. Similarly, dynamic path loss means suppose you are because as I said that wireless body area network supports in dynamic topology. If you will continuously move your hand and you are trying to send data, data may lose many times and you are sending the data again and again and again. That is another the cause of this energy consumption. Okay. So exploiting redundancy and mobility in energy efficient communication of wireless body area network. So we did this first one. We try to reduce the redundant data. Okay. So how can you reduce the redundant data? This paper is published in 21st International Conference in Computing in ICD-10. It was published in 2020. It was her first paper in this domain. So data redundancy is a popular problem in wireless sensor network. Similarly, data redundancy is a popular problem in wireless body area network. So data sense in W-band is critical and it needs to be tested whether to reduce the data or not. Because I said that we generally use these sensor nodes in medical application. So whenever you are reducing the data, you have to check that whether you can do it or not. You have to check that whether you can, for suppose you have deployed many sensor node in an agricultural field. In that case, you can reduce the data. But if you have deployed the nodes in case of wireless body area network, means you are collecting the health status of a patient. So in such a case, like reducing data is a challenging. So we check it, and it is also possible that you can reduce the data in case of this, and we did this work. The next is site of communication in different network scenario. So as I already said that this person is working, I have attached like 8 sensor node. So in posture 1, you see this left leg and right leg. This leg is here, one is in the back side, and this leg is on the front side. And while walking, this leg is going forward and this leg is coming backward. Or that means the topology is changing. Okay. So in case of this body area network, generally we use line of sight of communication and non-line of sight of communication. When the nodes are in line of sight of communication, you will receive all the data. And when the nodes are on the non-line of sight of communication with the coordinator node, in such a case, some data may drop. Okay. So your data losses happen. So node 6 on the right palm is in negative non-line of sight of communication. So here in these two, node 6 is non-line of sight of communication with this coordinator node, and node 1 on the right cuff and N5 on left palm are in the line of sight of communication. So in this figure, we have discussed about the line of sight of communication and line of sight of communication. Then next is relay-based communication. As I already told that in W-band, we generally use at most 2-hop communication. Why I said you will learn from here. So as I said that generally we do communication in line of sight of communication. So suppose coordinator node is here and I have attached some sensor node on my any leg or any hand. So line of sight of communication will directly transfer the data. But non-line of sight of when my hand is going backward, it is non-line of sight of communication. In such a case, it will be difficult to transfer the data. Some data will lose. Okay, so how can you achieve that? With the help of the relay node, we can achieve that. So for this also we did some experiment. So what are the challenges? And another challenges in sleeping posture. So many times you have seen that you can sleep like this in such a way. Suppose I have attached one sensor on the heart of this person and maybe anywhere here, and this person is sleeping in this position continuously for 2 hours. That means you will not receive all the information like catch by the sensor node. Okay, because if you keep suppose in the table your mobile phone, and it will not catch all the information because this person is sleeping in this position for longer duration of time. So quality of signal QoS degrades in sleeping human posture because some parts of the patient body blocks the channel of the communication. That's why quality of signal degrades, and the coordinated node will not catch all the signals transmitted by this person. So a node is in disconnections remain disconnected until the person changes its position. So therefore, here we propose one relay host communication RNC, and we published this paper in Smart Health Elsewhere in 2022. So here we have shown the different postures, sleeping posture. We tested it in a real life scenario. In that room we kept only one bed and one table, one smartphone, and these are the nodes we have attached to the portion of the body, and we have tested this position: prone position, lying on right side position, lying on the left side position. Okay, so when you are this person is sleeping in this type prone position, means it's ulta sona. You understood that this picture is not that much clear. Then all the nodes except the node 1 is available. All the 2, 3, and 4, all these nodes are not available. So sensor nodes are keeping the signals, but it is this receiver node or this smartphone is not getting all the signals transmitted by these nodes. So the next work we did, optimum placement of relay node in W-band. We said that with the help of the relay node, we can solve that issue. Okay, when a person is sleeping for the long duration of time. But we have not discussed that at which position the relay node will be placed so that that relay node will catch all the information. Okay, so where to place the relay node in a W-band? Optimum placement of relay node in W-band for improving the quality of signal. So where to place the relay node in W-band? The side of the neck is a suitable place of the relay node. Here we have tested it. And we analyze the effect of change in site of communication due to human body orientation on the quality of signal of home-based indoor RPM remote patient monitoring system. So we have used LSB board. Okay, we have not used the sensor node that are very costly. We have used LSB mode for our experiment, and we kept our laptop on the table. And what we did, this is a revolving wheelchair. Okay, the person is sitting here. And we checked that the transmitter of the person is kept here while sitting in the front. When the transmitter and laptop is our receiver, when the transmitter and receiver is on the same side, this receiver will receive all the signal. And this is quasi line of sight. This is line of sight, quasi line of sight, non-line of sight communication. When this person will rotate, this is I'm keeping on telescope mode, and I'm sitting like this, and my laptop is on the back side. That is non-line of sight of communication. Then you will not receive the full signal. Okay, in that we have tested also. You will see this figure. So this is the broken links. So we have tested this receive signal strength and time. So these are the broken links when they are in opposite side, and these are when they are on both the same side. This is a continuous signal. Okay, so then we next, this is another paper. So in this, if you will see that we tested this and we say that this position is the best position. Okay, this position is the best position to keep the relay node. So when the person is sitting this way or that way, this node will send the signal to here, and this node will send signal to the coordinator node. So at most we are doing to have communication. Okay, the next is this will discuss this one, the studiation of breaking signal and continuous signal. Then power saving approach of a smartwatch for monitoring the heart rate of a runner. So in this one, like we check the heart rate of a runner with the help of the watch. Okay, so heart rate of the monitoring a smartwatch is a battery consuming process. We try to minimize that. Whenever the runner is running and you are catching all the signals, then continuous heart rate monitoring, if you are monitoring, your battery will die. within very short duration of time. So to solve this issue, so we try this approach. Our approach is prevent continuous HR sampling for running events without missing the important heart rate information. So here we try to, and also we'll do adaptive HR sampling here, and also we recover the missed data. Okay. So here the person is running heart rate transmitted continuously to the smartphone, and the smartphone is continuously transmitted, and the data is saved in the cloud. Okay. With the help of, we have also made some app application, and this application is showing this. The next is we did adaptive sampling rate of heart rate. So we did adaptive sampling. Instead of collecting all the heart rate data, we missed some data. We only collected data generated with information gap. We gave some gap, and after this gap, we are collecting the data, and then we regenerated the heart rate with the help of some regeneration system or machine learning algorithm we used here, and we regenerated the data. Then next, this much we spoke about the wireless body area network. Then I will switch it to another word, vehicular ad hoc network. So this work was done by my second PhD student, Vivek. So vehicular ad hoc network, or VANET. So vehicles are equipped with wireless device which are known as on-board unit, or OBU, and number of sensors like GPS device, radar, air quality sensors are connected. So these OBU attached with the vehicles communicate with each other and forms a network known as vehicular ad hoc network. So if we see that these are the vehicles on the road, and these vehicles are forming some type of network that is known as vehicular ad hoc network. Ad hoc network, I have not discussed the characteristic of ad hoc network. Ad hoc network is little different. We generally don't use the use of access point in ad hoc network. The nodes will communicate with each other, and the nodes will act as the router in case of ad hoc network. So features of VANET. VANET is a subclass of mobile ad hoc network having different characteristics. They're high mobility. So we know one name, mobile ad hoc network. So if the name is that mobile ad hoc network, why vehicular ad hoc network? Vehicular ad hoc network is also a subclass of mobile ad hoc network. But why do we need vehicular ad hoc network? What are the characteristics of the vehicular ad hoc network? High mobility. In mobile ad hoc network, suppose you are walking, or you are your speed is not that much while you are walking. Okay, but when vehicles are moving, the speed of the vehicles are very high. It's a high speed, high mobility. Vehicles have high mobility as compared to mobile nodes in VANET. The mobile ad hoc network is created by military ad hoc network. Military people first created this mobile ad hoc network for their use. Okay, and after later it got known by all the communities, and you can use how many places we use mobile ad hoc network. So in next is frequent changing topology, because vehicle speeds are very high, so topology will frequently change. It's very rapidly change compared to the mobile ad hoc network. Okay. VANET has many applications like traffic information, accident information, parking information, electronic toll collection, real-time video streaming, hotel and restaurant advertisement, that you can do with the help of vehicular ad hoc network. So in network communication, here I have shown one roadside unit. As I said that we generally don't use access point. We are thinking that we have deployed roadside unit, and this roadside unit, the vehicle will, the vehicle have some important data. It will transfer to this vehicular roadside unit, and these roadside units are connected to the internet. Okay, so roadside units play an important role in providing connectivity among the vehicles on the road. Vehicles send requests to its nearby RSU, and nearby RSU fulfill the request sending by the required data. Suppose you are going somewhere, and you are going from here, Ropar, to Chandigarh airport. So in between this road, while going, I want to know the traffic information. I have the road is bifurcated. Okay, after you go and reach this point, you can go to Chandigarh in one way, and another way also you can reach the Chandigarh. But how come you know that whether you will get more traffic in this road or in this road? Okay, so that type of information you can collect from this vehicular ad hoc network. The roadside unit, if you are querying something to the roadside unit, and the roadside unit will answering you something. Okay. So vehicle send request to its nearby RSU, and the nearby RSU fulfill the request. When the number of requests get increased, scheduling algorithms are used to maximize the number of fulfilled requests. So for this also we need scheduling algorithm. So in rural area, RSUs are powered using the renewable energy. So I can say it is by solar power. Okay. So during variety of density of vehicle at different RSU, sometimes the power of this RSU will die fast, because all the vehicles, it is a dense area. Like all vehicles are requesting information to this RSU. So this RSU, the battery of energy of this RSU will die fast compared to this RSU. So how can you solve this issue? So due to varying density of vehicles at different RSU, some RSU are overutilized and some are underutilized. So this non-uniform energy consumption at RSU, this leads to low request fulfillment percentage. Okay. Then next is energy consumption. That for this we have written two methods. One is SCL method and the SCH method. I'm not. If you want to know more about this, you go and read the paper. So then next work is interest-based clustering. Suppose these RSU has these many vehicles, and some vehicle, while you are asking information, you are querying something. Someone is querying for the advertisement. Someone is querying for the, I want to go to this shop, whether this shop is present here or not. So these are different type of query. So RSU will get different type of query. So this query we can classify based, we can cluster this vehicle based on the query received from these vehicles. Okay, this we solve with the help of interest-based cluster. Then next is federated deep queue learning based offloading technique for vehicular fog computing. So for this we have used this fog computing, fog layer we have introduced, and this RSU layer are connected to the fog layer, and they communicate, and we increase the performance of this. So I'm not discussing in detail these things. Okay, so it needs one class to discuss with one method. I'm just giving you overview. So next we did one work on vehicular air pollution monitoring. This work we have published in Census. It's a ASTAR conference in 2008 with one of my intern students. I did this work. So what we did here, this vehicle is producing a lot of pollution. Okay. So in India, even if we have this pollution certificates, some vehicles produce a lot of pollution. Yes or no? So sensors and Arduino, with the help of sensor and Arduino, we just check how much pollution this vehicle is generating, and this, after sensing that information, we'll send this to the driver's smartphone. Okay. So what we did, we take one ESP32, we take some sensors, and we connected that near the silencer side of the vehicle, and we experiment this from IIT Ropar to Chandigarh airport, and this continuously collect the data and send this data to the mobile phone. Okay, so the driver has all the information how much pollution my vehicle generate while moving. Okay, so we did this experiment, and we also analyze this how much pollution generated. So this is the polluted air. This much pollution generated by my vehicle. This is the normal air. Okay. Next, real-time detection of defective IoT nodes. This work was done by one of my MS student, and he's now doing PhD from IIT Guwahati. So what we did here, how can you detect the presence of defective IoT nodes? So for this, we use this computer science building. We deployed many sensor nodes in many rooms, faculty room, as well as in lab area on different floor. We deployed many sensors, and sitting at the server, we can check that, which sensor is not working at this moment. Okay. If you will not get data, then that means that sensor is not working. But if all the sensors are died, these sensors are good, that means you can say that all these sensors are not working. Yes or no? So how can you know that which sensor is not working sitting and from the server? That we did here. So identification, real-time detection of defective IoT nodes. Okay. So another example of this, we can say that in a big agriculture field, we have deployed maybe 500 or 1,000 sensors. And how can you identify which sensor is not working at that moment sitting at the server? Because it is very difficult to go and check which sensor is not working. Yes and no? So we can do it by some algorithm sitting from the server. And so how we did it, first we initialize. So R is the root node and the root node is sending. Okay, all we are doing this in ad hoc network. We are not thinking that we have access point and we'll get everything. Okay, all this we are doing in ad hoc network. So this is the router node, and the router node will send some beacon message. First, it will create the network topology, and then you will get the data. So these two nodes want to join root node parent. Then root node again. They both joined this root node. So they both join the root node. Then after that, this node is sending beacon message to its neighbor. It is already joined the root node. So this node has not joined. So this node will join. Then again, this node will send the beacon message to its own neighbor, and this node will join this node. Okay, this is already joined. So after this, you have created the topology. Then you will send the data. I have created the topology, you send the data to the root node. Root node means I'm saying the server. I'm sitting at the server, and I'm making that node as a root node. And I'm sending all information to my neighboring nodes. And these neighboring nodes are also connected to other nodes. So after some time, this node stops sending data. So how can we identify? So you have created three structures. And again, after maybe 1 minute or maybe 5 minutes, again you are checking whether you are creating a tree. So if these two trees are not same, that means one node is not working. So which nodes is not working, you can, by comparing that topology, come to know that this node is not working and this node is a defective node. So for any type, defective node, many types of defective nodes are there. Here in this case, we said that the sensor stops sensing the physical phenomena, or it may happen due to the battery die. If your battery will die, then also the node will not work. And next is software-defined network. My third PhD student, she works on the software-defined networking. So here in software-defined networking, we have two planes. One is data plane and another is control plane. So why do we need this software-defined networking? In internet today, we know this is the best effort service model. Different types of traffic are treated in the same way in case of internet. So here, suppose a constant growth in the demand of multimedia application, so many types of traffic will come. Video streaming, voice, video conference, online gaming, many types of traffics are coming, but the internet will treat all the traffics equally. So in case of, because we have data plane and control plane are both works in the same place. But in software-defined networking, our control plane and data planes are different. So here we propose policy-based framework to implement network policy to minimize the routing cost, which fulfill the quality of service requirement of traffic flow in SDN networks. Then max flow in mean cost. I'm just skipping this slide. This is not totally related to IoT. So I'm skipping this slide. It's a good approach. It is already you can use in IoT also, this multi-path routing. How can you divide this bandwidth? But the time is also less. So next we did other works. I have not shown my fourth and fifth PhD students' work, but later I will add the slides. So tinkering a lab, I developed first time at IIT Ropar in 2000. 817. Okay, I established this lab from the scratch. I purchased all the components, space, chair, table, all these things done by me for this tinkering lab. So what we did in tinkering lab, some of the projects I'll show. Prosthetic arm, posture correcting chair, talking mirror. You can see search in YouTube also. You will get some of the video. Some BTech students already posted some video. IoT based smart agriculture system, superior, etc. So this is done by your seniors. So some of the BTech students are here. Yes or no? So I have written the group member name. So what is the use of this prosthetic arm? The objective of this prosthetic arm is to use an artificial arm to replace or augment a missing or implanted arm of a person. So I don't know whether it will work or not. It's working. It's working. So I have to play it again. So it gone. Otherwise, it's difficult to explain. So it will see these parts we created within 3D printer. This is not very like good. They have created, but they have created, and we have attached some muscle sensor here. And if you are doing moving your finger like this, it will this arm also will do like that. Okay, so we made all these parts and then joined all these parts by some thread, and then we have attached one muscle sensor here, and with the help of Arduino Uno we are doing this. Okay, the next is load relief device. This one, I don't know. It's there. It's not coming. So this aim of this project is to create a develop a system for lower back bending load relief mechanism using the principle of lifting heavy objects by hands. Okay, instead of when you are lifting heavy objects by hand, sometimes you get some pain. Okay, so they created this.
There are people who have to work in a continuous crooked back bend position, or have to repeatedly bend their back, or have spine and back problems like kyphosis, slip disc due to workload, age, or lifestyle. So, to resolve this issue, we have designed this load relief device. Principle. Our model follows one of the basic principles of mechanical principle of leverage. A lever is one of the simplest machines known. Basically, it consists of two forces, an effort force and a resisting force, acting around a pivot or a fulcrum. The distance from the effort force to the fulcrum is the force arm, and the distance from the resisting force to the fulcrum is the resisting arm. At equilibrium, the product of the effort force and force arm is equal to the product of resistance force and resistance arm. Now, let us see how this principle is applied in the model and how the model works. This is our model,
This is the
load
model
relief device. Without wearing this model, the rotational force on the back while lifting an object will have a very high value. But with this model, the load
It's your
gets
own hostel.
distributed on the thighs and hence
Old mess.
reduces the rotational load at the lower back, hence relieving the person. As it follows the principle of leverage, so we define 3 points A, B, and C. A, the point of load, which is the chest here. B, the fulcrum, which is the lower back here. And C, the point of effort, which the thighs act as. When the subject bends down, a force F1 away from the body acts on the chest, and a similar force F2 acts on the thighs away from the body, and there is a net generation of momentum at the lower back whose value is F1 L1 minus F2 L2. So there is a reduction, a subtraction of the momentum, and hence the load, the rotational load is reduced. And we can find the values of F1 and F2 through four sensors which are connected on the thighs and the chest. Construction. First, measure all the dimensions necessary for the prototype. Then,
So you understood this, So also we did one posture correcting chair. So what we use that sensors, and the sensors we attach here in this board. We made some hole and attach the sensor, and we attach here that board totally we attach here, and it is not shown here. So when you are sitting in a bad posture for a long duration of time, it will give you an alarm. So how they are doing, because these are all proximity sensor, they are calculating the distance. Okay, so if you bend this side, they have written the algorithm, and at that time, if you are sitting in the posture for like maximum 10 minutes, then your computer will give an alarm saying that you correct your posture, correct your posture. They made it. Still, I have not added the video, but they made it. It will say you correct your posture. Okay, and you can also use like this. This may be like inbuilt with the chair. Then it will be smart chair. Yes or no? So next also, this is not done by me, but by any other profession. So this is gesture control motorized wheel vehicle. So with the help of your hand, you can control the wheel. Yes or no? Stop or go, etc. Gesture control motorized vehicle. So many more projects are also there. I don't know now. I'm not leading this. Initially, when it was developed, so I was the coordinator of this lab. Now I'm not the coordinator of this lab, so I don't know where many things we kept on Alvari inside for like showing to the visitors. But I don't know how, the lab is changed 2-3 times. So we did this type of works, and thank you all.